Hi, my name is David Manche, and I am a student in the Math, Science, and Technology Center at Paul Laurence Dunbar High School. My mentor for this project was Dr. Sean Bailey of the UK Mechanical Engineering Department. This project is based on designing and building a Raspberry Pi-based data logger. Here's a quick overview of what I'll be talking about during this presentation. To begin, I'll go through the introduction in which I introduce a few key terms that you need to know in order to understand my project. After that, I'll go through the engineering goals that needed to be met. I'll then talk about the methodology behind testing one of those engineering goals and the results and discussions on whether or not that goal was met. I'll go through the future work needed to meet the rest of the goals, and then I'll talk about the acknowledgements, the work cited, and then ask if there are any questions. Now, to begin, it is very important to understand what a UAV or an unmanned aerial vehicle is. A UAV, if you are unfamiliar, is essentially a drone. There are two types of UAV. There are fixed-wing UAV and there are rotary-wing UAV. Rotary-wing UAV is basically a helicopter or a quadcopter, and a fixed-wing UAV is similar to what you would traditionally consider a plane. And in this project, I used a fixed-wing UAV. Now, it's also important to know what a Raspberry Pi is. And if you are wondering why I specifically put Raspberry Pi instead of just data logger in the title of this project, it's because this project has to be differentiated from a very, very similar project with the same mentor from an MSTC alum from 3 years ago, where he used a Arduino instead of a Raspberry Pi. And you probably don't know the difference, but a Raspberry Pi is a single board computer with a general purpose input-output, and an Arduino is a single board microcontroller with a general purpose input-output. The difference here being that an Arduino is better suited for hardware applications and a Raspberry Pi is better suited for software applications. And since this is data collection, I considered this to be more of a data collection software application. So I consider a Raspberry Pi to be a better use rather than an Arduino in this project. And a Raspberry Pi is pictured on the right here. But for both of these projects, it's very important that in the end, you centralize the sensor data. That's the whole purpose of this project. Because right now, as it is, the system that is used in the mechanical engineering lab for the fixed wing drone is a bunch of different sensors collecting data separately. And all of that data has to be reconciled into an Excel file separately. And they don't necessarily log at the same times, and there is a pretty significant error of margin there. Whereas this project, the idea is that it creates one program where it sends out a signal for all of the data to collect in one big loop, one big push for all of the data sensors so that it basically collects all in one data point. It makes it more accurate, precise, and overall better. So the engineering goals in this project, first of all, it has to be Raspberry Pi based. That is the most fundamental part of this project. But also it has to contain the sensors that were contained by the Arduino project and the system before that, which includes the infrared camera, the barometer, the GPS, the inertial measurement unit, which basically measures a magnetometer, accelerometer, and a gyroscope. And then also LiDAR, which is light detecting and ranging. If you don't know what that means, it's very similar to radar, except it's light. Also important, simultaneous logging. That's the entire purpose of the centralization. And then, as highlighted, is high speed. High speed is what is tested in the methodology of this lab. After that, we have low cost because you want to have several generations in case there are failures, and then fully tested as with any engineering project. So the methodology of this project is very simple. Basically, it's in a Python script, and it creates a CSV file, which is comma separated value, basically just an Excel spreadsheet, but with commas in between all the values. And it creates this CSV file, starts a for loop, and then runs for however many iterations. In this case, I did 100 per trial. And at the very end, I inputted a pause function to pause for half a second, quarter second, 10th second, and 20th of a second. And I didn't know what to expect. Perhaps it would be exponential, perhaps it would not, and perhaps it would work exactly as it was supposed to. But basically, I did 10 trials of each in case there were some funky things going on. And then I recorded all of that data into CSV files and then graphed it in Excel. So what I found was that there was a 0.2 second latency in the program itself. And you might not know what this means. Basically, between the actual average time per program iterations, as pictured in the top right graph, versus the expected time per program iterations, there is a 20-second difference in between 100 iterations. So the expected time per iterations is essentially just the pause function multiplied by the number of iterations, because it pauses for that many seconds every iteration, and so you should expect it to only take that many seconds if there is no time at all in the software running. Of course, it's very unrealistic to expect 0 seconds for the program to run, but that would be the ideal situation. Now, what I found was that the actual time for every single data point was that after 100 iterations, it took about 18 to 20 seconds more, which, over 100 iterations means 0.2 seconds for each run of the program. And this might not seem like a lot, but it's actually a 2-meter gap if the fixed-wing drone is flying at 25 miles per hour. For a rotary wing drone, where it's suspended in midair and can hover, it's really not that bad. But because this application is for a fixed-wing drone, where constant speed is required to maintain lift, a 2-meter gap at 25 meters does not allow for a lot of precision and is quite a long distance. Also important, the high-speed goal was not met. So closer to 0 means there's more options. And basically what this means is, obviously, if you have the chance to, you want to go smaller, right? But if you go closer to 0, you don't necessarily want that much data. So you get more options on, how much time you put in between each iteration. And a 0.2 second latency does not give you much choice at all. And this is very bad. And except for LiDAR, because the LiDAR libraries would not import with the rest of them for some reason, it was being stubborn, all of the other goals were met. So for future work, there are a lot of things that could be improved, namely increasing the speed, first and foremost. So some things that could be done to do that. Changing the programming language is the very first and foremost thing to do, because Python is an interpretive programming language, whereas some other languages like C is a compiling language. And that means that C automatically goes through and basically compiles the script rather than line by line. And this would make a pretty significant difference over 100 iterations if Python is interpreting the same code over and over again. And that will definitely be worth looking into. And also on that note, the LiDAR sensor, while maybe the Adafruit sensors don't have libraries in C, the LiDAR sensor does. And ironically, that might make it work for the LiDAR sensor. Another option is upgrading the RAM. So the model of Raspberry Pi I have right now is the Raspberry Pi 3B+, and that has 1 gigabyte of RAM, and it typically happens to be very slow. There is a new Raspberry Pi out called the Raspberry Pi 4, which for the same cost as the Raspberry Pi 3B+, you can get 4 times the RAM. That would be definitely worth looking into. Also, because obviously the LiDAR sensor has not been connected directly, the LiDAR sensor is very important and needs to be added on after the speed of the general program is increased. And once that is done, it has to have customized settings, and that'll be a lot of trial and error involved in that. And then for basically the applications of this project of what could be done with all of this stuff, data visualization is a major thing for this project. The LiDAR sensor is essentially a glorified altimeter, but because it has 8 lasers at specific angles, you can measure a lot of data points at once. So you can create things called point clouds. Similar to a point graph on an XY plane, a point cloud is a point graph on an XYZ plane in 3D. And you can visualize the landscape and terrain of whatever you're mapping with your drone using a point cloud. And also an interesting part of this is with the program and all those sensors, you can connect the values of the data points and you can visualize them. So you could visualize the air pressure above a specific place on the ground, and you could visualize this in 3D, and it would be very, very interesting for geoanalytics applications. Another point of this is photogrammetry, which would allow essentially attaching a camera to the system. There is a camera on the current system, and cameras for the Raspberry Pi are very easy to connect. While not necessarily high quality, it would be definitely worth looking into because you could essentially map the terrain with an actual map, and that would definitely be worth looking into. So for this project, I'd like to acknowledge first and foremost my mentor, Dr. Sean Bailey, and then Ms. Karen Young, the leader of MSTC, and of course, Math Science and Technology Center for giving me this opportunity, and then the Kentucky Young Researchers Program. And any questions? Thank you for coming to my presentation.